Good morning and welcome. So, you have already studied detailed analysis on distributions and its various properties. Now, in this next set of lectures, maybe around 6 or 7 lectures, we are going to introduce two of the fundamental very important operations, namely Fourier transforms and convolutions. You have already seen somewhat an extensive introduction of the Fourier transforms in the preliminaries. So, the aim is to define Fourier transform of distributions now, and again the convolution of distributions. So, maybe we will do little more, since convolution is not done much of functions, we will do little more on functions, and then eventually the idea is to define for distribution. Why it is important? Probably the Fourier series, as you know very well, transforms and convolutions plays a vital role in the analysis of PDE. As you know, Fourier series was introduced in the beginning of the 19th century by Fourier in the process of studying one dimensional heat equation, and former Fourier series to represent a function in the form of an infinite series. Since the concept of convergence, integration were at its primitive stages, even the proper definition of functions, because the modern set theory was not available, justification of Fourier series opened up many questions to the mathematical community. Nevertheless, Fourier series introduced the Fourier introduced the so called Fourier coefficients to obtain the series and eventually the series thing. But actually, if you are really looking at it, Fourier series was in the concept was generated 50 years prior to Fourier in the 1750s by Bernoulli, again in the process of studying wave equation. Fourier was looking into heat equation, and the first PDE introduced by D'Alembert, all that, which you have seen these extensive lectures in our course on partial differential equations, first course. The application of Fourier series and convolutions are not limited to just PDEs. There are many applications in signal processing and other things, and inverse problems and all that, and you have reasonably understood very well about that one. Okay. So, the Fourier series and convolution, even though two operations, the collective way of using Fourier series, Fourier transform and convolution is a potent weapon in our analysis, many analysis, not only as I said in PDE, and so it is important for the distributions, but because we are looking for solutions and the derivatives not in the standard form, in the weak form in the concept of distributions. So, it is important to study this one. So, let me so the Fourier transforms, maybe we will use it Fourier transform and convolutions. We do a natural process of doing this one. So, let me quickly recall what is given in your introduction. Okay, some of the thing we will do that one. Okay. If f is in L1, you have seen that. So, I will not elaborate anything. It is in Rn, then you know that implies f hat is Fourier series. Whatever be the way you define, there are different books will define in different ways. The only difference is taking coefficients, whether you want to put a coefficient, no coefficient, put the coefficients in the exponential term, accordingly some constant you have to deal with it, that is all. Okay. F hat is in L infinity, need not be in L1. This was the need not be in L1. So, unless f hat is in L1, we want to recover f hat f in terms of f hat. The idea is that recover f via in some sense, in some way, the Fourier transform of f hat. Okay. Maybe some change. Recover f hat f from f hat. This is what is called the inversion formula, and hence inversion is not possible immediately for start with an L1 function, because it is f hat in L1 and need not be in L1. So, you cannot get back f immediately. That is a one message. The second thing is, if f is in L1 intersection L2, I do not write Rn, it is always Rn, not on omega, it is in the full space. If L1 intersection L2, then the beauty is that f hat is in L2, so that you get it, and you also get an isometry norm f hat at L2, which I write it like this one, this is L2 of omega, okay, is in L. Of course, there may be a coefficient here, no sorry, it is not in omega. So, it is better not to write omega, it is in Rn. Okay. So, there may be a coefficient here if you use a different formula. So, do not worry, that is not an error coefficient, depending on the book, okay, what formula. So, the way it is given in preliminaries, you get the constant to be 1. Okay. So, different books, it does not matter, it is not an error if you see a constant, only there may be a minor difference in the definition. Okay. So, you get that one. So, that gives the Fourier transform f is an isometry L2 to, and then you can extend the Fourier transform to L2 as an isometry. May not be by the formula, but then you are not far from formula, you got approximations everything. Okay. So, you got up to L1 and L2, you have the Fourier transform. Now, the question is that what about if f is in L3, f is in L3, L4 etc., can you define the Fourier transform? Because the main thing you tool used in f hat is its isometry and density. Just density is not enough, you need isometry. So, with that isometry you could extend it, or more generally for t in d prime. So, you want to for t in d prime, how to define t hat, that is the question we are going to ask. So, once you know t is the t in d prime, you can define a distribution, it is a Fourier transform, then immediately L3 Ln are all in d. So, you can do that. So, immediately. So, it not only defines the distribution, it defines the many functions you can't do not know how to define distribution. So, we are going to see the Fourier transform of L3 L4 functions not as functions, but as distributions. So, it is the thing we will do that. So, so you recall LP, that is what exactly is that LP is contained in D prime, you know that. So, what we are going to see is we cannot define this as you see, even for Fourier transform defining from functions are difficult for every function. So, definitely you cannot expect Fourier transform to be defined for all distributions. So, we will see what is called a special class of distributions, which you are already seen, okay, known as tempered distributions. Okay. Okay. And that will be the class where you will be defining the Fourier transform, and that tempered distribution contains all the LP spaces. So, that way you can extend your Fourier transform concept to general thing. So, all right. So, let us do something. How do we go about it? If you again follow the philosophy, if you want to define the distribution, the Fourier transform of distributions, first you see whether you can get a formula of the Fourier transform of the function, the Fourier transform given by a function for which the Fourier transform is defined. So, if you can get a formula, that should be the possible formula if there is a validity. So, let us follow that one. Okay. So, take the motivation, this is a motivation of a formula. That is always we are doing it, that is what we will do it even for convolutions. First look at if you have a convolution, you already have a Fourier transform for functions, and let us see how it behaves if you treat it as a distribution. So, let us take f wherever it is. I am not even taking where it is, wherever the formulas are applicable. So, you take f and then assume that f hat exists, and assume that f hat is also locally integrable or whatever it is, because we want to understand locally integrable f hat also. So, f hat is defined and f hat is if you want to assume whatever smoothness it is or whatever thing, so that whatever formulas I am going to write are valid. Okay, because whenever you extend it, the existing validity should be there. So, that is what we will say. So, for phi in d of r, right? So, let us look at the distribution given by T f hat. That is what the formula will give you. Your T f hat should be, our thing is that this should be your T f hat. This is our wish, right? Should be like that. If at all there. So, the distribution given by f hat should be the same as the distribution, the Fourier transform of the distribution given by f. It should coincide, and that is the formula we are looking at it. So, you look at your T f hat acting at phi is equal to integral of R n f hat of psi phi of psi d psi. So, write down your formula. So, you have integral f of x e power minus I x I d psi dx of d psi. Of course, in your preliminary you used a constant here. So, if you are using that constant, follow that constant. So, for me it is only a motivation each time. So, I used without any constant. Yes, but then you do not have exactly the there will be a coefficient when you write norm f hat, some constant into it. But that is not the thing for motivation. So, you use that one. So, you use Fibonacci now. When you use Fibonacci, you will have f of x here, and then you will have there is a phi of psi d psi here. So, you will have phi of psi e power minus I x I your d psi of dx Fibonacci. As I said, do not worry about the validity, later all when you want to check it. So, this is nothing but integral of f of x phi hat of x dx. So, as a distribution, so T f at phi hat, you see. So, you have that implies T f hat acting at phi is equal to T f acting at phi hat, you see. So, a possible formula, a possible or a natural formula, possible or natural formula. If this is valid, if valid, right, that I want to say. Now, I will soon come valid. Natural formula would be T hat at phi should be T acting at phi hat. So, that is a natural formula. Now, what is the problem here? Is this meaningful, valid? That is the thing. Valid only if, of course, if f is nice, it may be valid, but I do not want to say in general valid. It can be valid sometimes, but in the normal way the distribution you want if phi hat is in D of R, okay. Because the TF acts on as a distribution, then it acts on D of Rn functions. So, what do we do? So, the question is that if phi is in D of Rn, you may get smoothness. The problem is that does this imply your phi hat is in D of Rn? But so that is a question, that is a big question. At least even for some class of functions of D of Rn, can it be phi hat in? But the answer is that it is never. So, this will not happen, not only for function, no function it will happen, this will never happen. Unless phi is identically 0. So, when you have a function, non-trivial function which has a compact support, phi hat will not have compact support. This is due to the, I will just state here, the famous theorem called Paley-Wiener theorem. Of course, I will not prove here. So, maybe you can look into so many books, maybe since I am giving a standard reference, Rudin, of course, functional analysis, Rudin book. So, you will see the theorem proof and all that, much more material there doing it. Okay. So, what is this Paley-Wiener theorem? Let phi is in D of Rn, with and let support of course the support of is compact. Since support of is in compact, you can put it in some ball of radius 0. Okay. So, you can always put that ball of radius 0 for some r positive. Okay. And then you can define a function f of z. Z is a complex number, and integral of Rn phi of x e power minus I z x dx for all z in C is an entire function in Cn, is an, that means analytic in Cn, entire function in Cn, the complex and satisfying the estimate is a little deep theorem. Satisfying the estimate modulus of f of z less than or equal to some constant which may depend on, and you get some decay estimates. This is basically your decay estimates of order m. Okay, up to order m you get some decay estimates into exponential of r modulus of imaginary of z. Okay, so this is an estimate, you get it. Okay, so you have an estimate on that function. So, it is an analytic function, and this one. The interesting thing is that the converse is also true. Conversely, if f is an entire function, entire function on Cn satisfying star is nice to read at least one such theorem, satisfying star and satisfying the estimated star, then f is given by the above formula. F is given by, so let me call this star, maybe this is double star and this is so double star, then f is given by star, okay, for some phi, there exists a phi, for some phi in D of R. Okay. So, you see, so every compactly supported function generates an analytic function with some decay estimates, polynomial type decay estimates in that one. As an immediate remark, so let me use a different color, maybe immediate. If z equal to x, z equal to or xi is real, then your f of xi is equal to integral of phi of x e power minus I x dot psi dx. This is nothing but except for the constant. If you used a constant, there will be a constant, which that constant can be merged with the phi also. That will not affect that one. Okay. So, it does not matter. This is nothing but phi hat of psi. Okay. So, what does this imply, this thing? So, this implies, the above thing implies your phi hat is the restriction of an analytic function, of an analytic function and hence it cannot have, because the zeros of analytic functions are discrete. So, it cannot vanish on outside a compact set, and hence unless phi itself is 0, hence phi cat cannot vanish outside a compact set, cannot even vanish except at discrete point outside a compact set. You see, unless phi identically 0, in that case your f is 0, everything is 0. So, there is nothing more to work on that one. Okay. So, what do we need here? So, that is what, so how do we do that one? So, you cannot have T phi hat. So, because phi hat is can never be in here. So, we have to look for a space. So, you have to look for distribution. So, that immediately implies you will not be able to define distributions for the Fourier transform of all distributions, because we need phi and phi hat somewhat in the same space to do that. So, the question is that we need to, look for distributions, look for T distributions in D prime which can be extended to a bigger space, which can be extended to a bigger space x containing d omega. Okay. And this process you have already seen. One possibility is T with compact support, T with compact support, In this case t can be extended to x equal to your C infinity of omega to r. That means, and you realize t is a the dual of that space. So, these are all the distributions with a compact support can be extended to a bigger space. But there is a catch here. If phi is in C infinity of omega, then phi hat need not even be defined, because phi hat cannot define the for C infinity. These are all in Rn. Okay. Yeah, we are working with everything in Rn for the time being. So, Rn. It does not matter, I told you already that d prime of Rn. So, Fourier transform theory, right. So, you know, Rn. Omega is Rn, I can define that way. Okay. Then phi hat, because may not be defined. So, may not be defined. Okay. So, that forces we are looking for some x space such that d omega contained in x and contained in C infinity of omega, and which will hopefully will give C infinity of omega dual, and that is E, the notation E is used. Distributions can be extended up to this one contained in x prime and that contained in t prime, and this is the space which we will, you already seen some of the aspects of it. This is the space of short space which plays you an interesting role, short space, and I will give you quickly some which also you already seen. So, I will quickly give the recall the definition, because this is important. So, some repetition is okay. You may see some few, and this t with in d prime, that means t is defined in d omega, which can be defined for the extended to x or the short space zeta are called tempered distributions. Such distributions you will see even by that name. So, tempered distributions. So, I will have a couple of minutes more. Okay, so maybe so what is your short space which we are going to define? Maybe we'll define something. Yeah, so I will quickly recall before going to do that one. So, where is my definition? Short space definition I will be giving. Yeah. Okay. So, let me recall what is quickly the short space. So, okay. Short space basically is the set of all f in C infinity of Rn such that modulus of x power alpha t per beta of f going to 0 as mod x tends to infinity. This is for all multi indices alpha beta. Such functions each f. So, let me start with one more definition, probably this may not be defined earlier. A function, a C infinity function, actually C infinity needed, but we are working only on that. C infinity function f on Rn is z to be rapidly decreasing if there are constants mn or mm, maybe I will use it mm, m equal to 1, 2, 3 etc., such that so you can estimate, okay, modulus of f of x is less than or equal to mm into mod x power minus n for as mod x tends to infinity. So, you have a decay. So, there is a rapid decay of the polynomial type, that is what I said. So, it decays then the every polynomial it decays. So, if okay, so what we are saying that in zeta you are looking for rapidly decaying functions for and functions which are rapidly decaying, and all its derivatives are also rapidly decaying. So, the Schwarzschild functions are those infinity functions for which f and all its derivatives are rapidly decreasing. Okay, that is so there is a no, see d omega, you keep that in mind. In d omega you have a compact support. So, it is already decayed to 0. Here now you are looking at the rapid decay for rapid decay only. So, for C infinity functions you may not have any decay. So, I will just write a property and then I will stop it, because this property also probably done, but the property is easy. F is in zeta, I may use if and only if P LF is bounded in Rn. These are all small exercises actually, you will see bounded in Rn. I will leave this as an exercise for you. You should work out, because this is the first time you will be seeing this material. This is for all polynomials P and for all linear operators with constant coefficients, okay, linear operators, linear differential operators, okay, linear differential operators with constant coefficients, constant. These are all almost trivial, but it is important to write down and learn it. Okay. That means sigma a alpha d power alpha mod alpha less than or equal to m. P is the polynomial. Okay. For this, and this is also equivalent to, these are all fine, but it is nice to have some verifiable condition, and this will be very useful in your verification or proving certain things. 1 plus mod power k. So, I am looking at that d power alpha of f is bounded. You do not have to check for boundedness for everything, all polynomial is enough to check for boundedness with this polynomial for bounded for all k greater than 0 and for and for all alpha. Okay. And so, you should see the so I think I will okay. If I start something I need more time. So, thank you very much. So, we will continue with this motivation, and then we will quickly see how to define Fourier transform of distributions with a definition we already seen. So, it is only we have to see that the validity, and we will recall that the Fourier transform is an isomorphism. It is an isometry on zeta, L2 isometry on zeta. So, phi is in theta, phi hat will be in theta, which you are already seen it in the preliminary lectures. Thank you.